Welcome, everyone. I'm glad you're here today. We're about to dive into an important topic, wastewater disinfection training. This presentation will explore how we can effectively remove or kill disease-causing microorganisms in wastewater. Over the next few slides, we'll cover the reasons why disinfection is essential, different methods used, and best practices to ensure safe discharges. Let's get started. Let's talk about why disinfection truly matters in wastewater treatment. Now, the challenge we face is that even after various treatment processes and natural die-off, many pathogenic microorganisms can still remain in the wastewater. This is why disinfection is so critical. It's the step that ensures we effectively eliminate almost all of those harmful microorganisms. A key point to understand here is the distinction between disinfection and sterilization. Disinfection is designed to destroy all pathogenic microorganisms, which are the ones that can cause disease. Sterilization, on the other hand, goes a step further. It destroys all microorganisms, including those that are harmless or beneficial. In wastewater treatment, our goal is disinfection, not sterilization. Complete sterilization isn't necessary and would be impractical and cost-prohibitive in this context. So, understanding this difference helps us appreciate the purpose of our disinfection processes and how they fit into the overall goal of creating safe, clean water. Let's take a moment to look at the main objectives of disinfection. First, when we talk about public water supplies, the goal is to protect drinking water sources from contamination. This is especially important when we're dealing with treated wastewater that could carry harmful microorganisms. Next, for recreational waters like lakes, rivers, and beaches, disinfection helps ensure that these waters are safe for activities like swimming and boating. Nobody wants to worry about catching an illness while enjoying a day outside. Then, we have shellfish growing areas. These are critical because shellfish are harvested for human consumption, and maintaining their safety involves safeguarding the areas where they grow from contamination. One key point to remember is that disinfection, particularly chlorination, is highly effective because pathogenic microorganisms, those that cause disease, are much more sensitive to chlorination than non-pathogenic ones. Essentially, chlorination can kill almost all pathogens in wastewater without the need to sterilize the entire effluent completely. This targeted approach makes disinfection both efficient and practical in protecting public health and ecosystems. Let's talk about why chlorine is considered the standard in disinfection. Chlorine is the most widely used disinfectant, and there are a few reasons for that. First, it's readily available, meaning it's easy to access and distribute where needed. Second, it's simple to apply, whether you're treating water or surfaces. And finally, it's cost-effective, cheaper than other oxidizing agents like potassium permanganate, chlorine dioxide, or ozone. These factors make chlorine a practical choice for many applications. Now, when it comes to how we use chlorine, there are three main forms of application. We can use chlorine gas, which is effective but requires careful handling. Or there's chlorine powder, commonly known as HTH, which is easy to store and use. Lastly, we have aqueous solutions, such as chlorine bleach, which is widely used in household and industrial settings. Each form has its own advantages depending on the situation. One of the most impressive features of chlorine is its high effectiveness. Even at relatively low dosages, chlorine can destroy a broad range of pathogens very efficiently. This potency is a key reason why it remains the standard in disinfection practices worldwide, supporting our overall goal of maintaining safe, healthy environments. Let's talk about how chlorine reacts in wastewater. Chlorine can be added in different forms, such as free chlorine, which is Cl2, hypochlorite ions like alkyl-, or chlorine dioxide, ClO2. No matter the form, chlorine is highly reactive and acts as a strong oxidizing agent. This means it can effectively kill bacteria and other pathogens, but its reactivity also leads to some important side reactions. Now, before chlorine can do its main job of disinfection, it often reacts with other substances present in the wastewater. These are what we call side reactions, and they happen quite quickly because of chlorine's high reactivity. These reactions can involve organic materials, hydrogen sulfide, phenols, thiosulfate, and ferrous iron. Essentially, chlorine gets used up in these reactions first. This brings us to the concept of chlorine demand. Because of these side reactions, a significant portion of the chlorine is consumed before it even reaches the pathogens we want to eliminate. Understanding this helps us determine how much chlorine we need to add to ensure effective disinfection. It's a critical point in optimizing wastewater treatment and making sure the process is both effective and efficient. Let's take a closer look at some essential chlorine treatment terms. First, the basic unit of measurement we use is either milligrams per liter, or mg/L, or parts per million, ppm. These are very small units, but they effectively reflect the concentration of chlorine in water. To give you a sense of scale, 1% equals 10,000 mg/L or ppm. So we're talking about tiny amounts, but even these small quantities are crucial for proper treatment. Next, we have chlorine dosage. This refers to the amount of chlorine we add to the water. It's usually determined by considering the pounds of chlorine used and the total millions of pounds of water we're treating. Getting this right ensures effective disinfection without overdoing it. Finally, there's chlorine demand. This is a key concept because when chlorine reacts with substances like iron, manganese, hydrogen sulfide, organic compounds, or ammonia, it loses some of its disinfecting power. So the chlorine dose must always be higher than the demand, meaning it must be enough to react with these substances and still leave enough chlorine available to disinfect effectively. Connecting this to our overall theme, understanding these terms helps us optimize chlorine treatment, making sure we're using the right amounts in the right way to keep water safe and clean. Let's take a closer look at understanding chlorine residuals. First, what exactly is residual? Well, it's the chlorine that remains in the water after it has reacted with substances that demand chlorine. In other words, once the chlorine has done its job reacting with contaminants, the leftover amount is called the residual. To find out how much residual chlorine there is, we subtract the demand from the initial dosage. For example, if we add a dosage of 4 milligrams per liter, and the demand is 2.5 milligrams per liter, then the residual chlorine would be 1.5 milligrams per liter. This remaining chlorine is what continues to disinfect the water as it travels through the system. Now let's talk about the types of chlorine residuals. The first is the free chlorine residual, which mainly consists of hypochlorous acid, or HCl. This is the primary disinfecting agent that keeps the water safe. It's very effective at killing bacteria and viruses. Then we have the combined chlorine residual. This forms when chlorine reacts with ammonia or other nitrogen compounds, creating chloramines. While chloramines also have disinfectant properties, they are generally less effective than free chlorine. Understanding these residuals is crucial because they help us ensure ongoing disinfection and water quality. They also tell us how well our chlorination process is working and whether adjustments are needed to maintain safe, clean water. Now, let's look at the difference between free and combined chlorine residuals. When we talk about free chlorine residual, we're referring to the chlorine that remains in the water after it has reacted with any demand. Basically, once the chlorine has done its job to disinfect, it reacts with water to form hydrochloric acid and hypochlorous acid. The key here is the hypochlorous ion, or HCl-, which we measure to determine the free chlorine residual. This form of chlorine is the most effective for disinfection because it's available and active. On the other hand, when ammonia is present in the water, things change a bit. The hypochlorous acid reacts with ammonia to form chloramines. These are what we call combined chlorine residuals. Now, chloramines are weaker disinfectants compared to free chlorine, meaning they require longer contact times and higher concentrations to achieve the same level of disinfection. Chloramines can exist in 3 different forms, depending on how many chlorine atoms they contain: 1, 2, or 3. For example, monochloramine has 1 chlorine atom, dichloramine has 2, and trichloramine has 3. While they're less powerful disinfectants, a notable advantage is that chloramines tend to stay in the system longer because they don't break down as quickly as free chlorine. Understanding these differences is crucial for maintaining effective water disinfection and ensuring safe, clean water for everyone. Now, let's talk about how environmental factors can influence the effectiveness of chlorine. First up, temperature effects. When temperatures are colder, chemical reactions tend to slow down. This means that in colder water, we often need higher chlorine concentrations and longer contact times to achieve the same level of disinfection. It's important to keep this in mind, especially in winter or in colder climates, to ensure our disinfection process remains effective. Next, we have pH impact. When the pH of the water is high, it actually makes it more difficult for hypochlorous acid to form. Since hypochlorous acid is the active disinfectant, a high pH can reduce chlorine's effectiveness. To compensate, we need to increase the dosage of chlorine to maintain the proper residual level for effective disinfection. Understanding these environmental factors helps us optimize our disinfection process, ensuring we maintain safe and clean water regardless of external conditions. Let's talk about breakpoint chlorination. Since ammonia is present in all domestic wastewaters, understanding how it reacts with chlorine is really important. When we add chlorine to water containing ammonia, it doesn't just stay as free chlorine. Instead, it reacts with hypochlorous acid, or HCl, to form different chloramine compounds: monochloramine, dichloramine, and trichloramine. Now, the key here is the breakpoint curve. This curve shows us how chloramines are formed and then destroyed as we add more chlorine. Initially, as we add chlorine, chloramines build up, but if we keep adding, eventually, the chloramines are broken down and free residual chlorine is achieved. It's important to remember that each water system has its own breakpoint. This varies depending on the chemical makeup of the wastewater and how much chlorine demand there is, meaning how much chlorine is needed to reach that free residual level. So, understanding this process helps us optimize disinfection and ensure that we're effectively treating water while minimizing chloramine formation, which ties back to our overall goal of safe and clean water. Let's take a closer look at understanding the breakpoint curve. First, at point A, which we call the initial reaction, when we start adding chlorine, it immediately reacts with the ammonia already present in the water. This creates a combined residual reading, and as we increase the chlorine dosage up to about 2 ppm, we see this residual level rise accordingly. Next, at point B, known as the chloramine destruction point, the combined residual begins to drop. This happens because the chloramines, these are the compounds formed when chlorine reacts with ammonia, are being broken down. This process continues until we reach the breakpoint. Now at point C, which is the breakthrough moment, when the dosage hits around 3 ppm, the breakpoint occurs. Here, we finally see the first free chlorine residual appear. This is a key indicator because beyond this point, the free residual increases at the same rate as we add more chlorine. It's also important to note that even after reaching the breakpoint, some combined residual might still linger, but it will stay at a minimal level as long as we keep the dosage above 3 ppm. Understanding this curve helps us optimize chlorination, ensuring effective disinfection while managing residuals efficiently. Today, I'll be talking about testing for chlorine residuals, which is essential for ensuring water safety and quality. One of the most convenient and repeatable methods we use is amperometric titration. Although it involves higher equipment costs, it's the most common in laboratory settings because of its accuracy and reliability. Next, I want to mention the OTA test, or orthotoluidine arsenite. This was once the industry standard until the mid-1970s. However, it's no longer in use today because of interference issues and the fact that arsenite is carcinogenic, making it unsafe and less reliable. Currently, the standard method we rely on is the DPD test, or diethylphenylene diamine test. It's well suited for fieldwork since it's straightforward and quick. The process involves colorimetric analysis, where we use two chemical packets, one for free chlorine and one for total chlorine. The test works by comparing the sample's color to a color wheel. If chlorine is present, the sample turns pink or red, and by subtracting the free residual from the total residual, we can determine the combined chlorine residual. Overall, the DPD method provides a practical and accurate way to measure chlorine residuals on site, helping us maintain safe and effective water treatment processes. Let's take a closer look at the common forms of chlorine used for disinfection. First, we have chlorine gas, or Cl2. It's typically compressed into a liquid form for easier storage, often in large cylinders weighing 150 or 2,000 pounds. One of the key advantages of chlorine gas is that it's the most cost-effective option on a per-pound basis, making it a popular choice in many applications. Next, there's chlorine powder, known as HTH or high-test hypochlorite. Its chemical name is calcium hypochlorite, Ca-2, and it contains about 65 to 70% available chlorine. While it's more expensive than chlorine gas, about 2 to 3 times the cost per pound, it's often used because it's more stable and easier to handle in certain situations. Finally, we have chlorine bleach, which is a liquid solution of sodium hypochlorite, NaOCl. This form usually contains between 3 and 12% available chlorine, with the rest being water, around 88 to 97%. It's the most expensive form of chlorine, but it's widely used because of its convenience, especially in household and small-scale applications. Connecting all these forms to our overall theme, each has its unique advantages and costs, and choosing the right one depends on the specific needs and circumstances of the disinfection process. Let's talk about some critical safety information regarding chlorine. Chlorine is a greenish-yellow gas, and it's actually about 2.5 times heavier than air. That means it tends to stay close to the ground, which is important to remember in case of leaks. It's very corrosive, so when it comes into contact with moisture, whether in water, on your skin, or even in your eyes and lungs, it turns into hydrochloric acid. That's what makes it so dangerous. Now, while chlorine doesn't support combustion, it can still pose serious health risks. In small amounts, inhaling chlorine might cause irritation, but larger doses can be fatal. That's why safety is absolutely paramount when handling this substance. We need to be vigilant because accidents involving chlorine gas can harm workers, the public, and the environment. Remember, always prioritize safety first whenever working with chlorine. Proper handling, protective equipment, and awareness of these risks are essential to prevent injury. This slide underscores the importance of respecting chlorine's hazardous nature, which ties back to our overall theme of safe chemical management and ensuring everyone's well-being. Let's take a closer look at the safety requirements for the chlorinator room. First, the room should be designed with safety in mind, including a window in the door so you can see inside without entering. This helps you assess the situation before stepping in. Additionally, switches for lighting and ventilation should be placed outside the room, making it easier and safer to control these systems without unnecessary entry. Ventilation is especially important here because chlorine gas is heavier than air, so the room needs floor-level ventilation to effectively remove any fumes and prevent dangerous buildup. When it comes to temperature control, maintaining a range between 60 and 120 degrees Fahrenheit is crucial. If it gets too cold, below 60 degrees, green ice can form, which can clog equipment and cause operational issues. On the other hand, if temperatures rise above 157 degrees, there's a risk of cylinder rupture, which can be catastrophic. Now, a key safety rule that I want to emphasize: never enter a chlorine facility without ventilating it first, and this should be done for several minutes. Proper ventilation is essential to clear any residual gas. For new facilities, this process should include scrubber systems with backup power, ensuring continuous safety even during power outages. Following these precautions helps protect everyone and keeps the system operating safely and efficiently. Let's talk about chlorine storage and cylinder safety. First, it's really important to keep the storage room dry and well ventilated. This helps prevent any buildup of fumes and reduces the risk of accidents. Always store chlorine separately from other chemicals to avoid any dangerous reactions. It's also essential to keep empty cylinders separate from full ones. This helps prevent confusion and ensures safety during handling. When cylinders are not in use, make sure they are chained to the wall. This prevents them from falling or being knocked over, which could cause leaks or injuries. Now, regarding handling the cylinders, never remove the valve hood unless the cylinder is securely chained to the scales and ready for use. This is a crucial safety step. Additionally, emergency repair kits should always be available nearby to quickly contain any leaks should they occur. Moving on to safety features, each gas cylinder is equipped with a fusible plug. This is a safety device designed to melt at around 157 degrees Fahrenheit, which helps prevent the cylinder from rupturing in high heat conditions. For example, 150-pound cylinders typically have one fusible plug in the valve assembly, while larger 1-ton cylinders have 6, 3 on each end. Recognizing these safety features and following proper storage and handling procedures is key to maintaining a safe environment and protecting everyone involved. Let's talk about handling and respiratory protection when working with HTH. First, it's crucial to store HTH in a cool, dry place, separate from other chemicals to prevent any unwanted reactions. Remember, never allow contact with petroleum products or organic solvents because that can cause a violent explosion, which is extremely dangerous. Always avoid contact with your eyes or bare skin to prevent burns or irritation. Now, for emergency situations, we have gas masks designed specifically for escape purposes only. It's very important to understand that these masks are not meant for entering areas where chlorine gas is present. If oxygen levels drop below 12%, survival becomes impossible even with filtered air, so safety is paramount. Also, change the canisters every 6 months or after any exposure to ensure they remain effective. When working directly in a chlorine gas environment, you must use self-contained breathing apparatus, or SCBA units. These units provide about 30 minutes of breathable air and are essential for safe entry. Keep in mind, the alarm on these units rings at 500 psi, which indicates roughly 5 minutes of air remaining, so always plan accordingly. It's important to remember that chlorine gas reacts with eyes and lungs to form hydrochloric acid, which can cause severe injuries or even death. Plus, damage from chlorine exposure is cumulative, meaning multiple minor exposures can lead to serious health problems over time. So, always prioritize proper protective measures to stay safe and protect your long-term health. Now, let's take a closer look at gas chlorination systems. A typical setup involves gas cylinders that are connected to a gas chlorinator. The system includes a pressure-regulating valve to control the chlorine pressure, a feed rate indicator to monitor the amount of chlorine being fed, a flow-regulating device, such as a V-notch plug or needle valve, and an injector or ejector that helps draw the gas into the system. One key component here is the chlorine pressure-regulating valve, or CPRV. It opens when vacuum is created by the injector, ensuring safe and controlled delivery of chlorine gas. When it comes to feeding rates, for a 150-pound cylinder, the maximum flow rate is about 40 pounds per day. For larger 1-ton cylinders, the maximum is around 400 pounds per day. Exceeding these rates can cause problems because the tanks tend to frost over. That's because heat can't pass through fast enough to evaporate the liquid chlorine into gas. Interestingly, though, with ton cylinders, you can feed liquefied chlorine using evaporators without any limit on the removal rate. Understanding these limits is crucial for maintaining safe and efficient operation while ensuring effective chlorination. Let's take a closer look at hypochlorination and some alternative disinfection methods. Starting with hypochlorination systems, these typically include a solution tank that holds at least a 1-day supply, a diaphragm-type chemical feed pump, and a T fitting into the well line. The bleach used here usually contains between 5.25 and 12% available chlorine. For example, if you're using HTH solution, you'd mix about 1.5 pounds of it per gallon of water to get roughly 1 pound of chlorine per gallon of solution. Moving on to mixed-oxidant systems, these are a bit more advanced. They involve on-site brine generators that have day tanks and automated injection systems to produce the mixed-oxidant solution right there on site. The key component is an electrolytic cell that uses sodium chloride, water, and electricity to generate the disinfectant. One major advantage of these systems is safety. They're considered safer than traditional chlorine because there's no need to transport or store hazardous chemicals. This also means you don't require hazmat training or a risk management plan for these systems. However, it's important to be aware of potential issues with feed pumps, especially check valves. These can clog up with lime deposits, particularly when using HTH, which contains around 30–35% lime. To prevent this, it's best to place strainers a few inches above the tank bottom, which helps keep clogs and fouling at bay. Overall, understanding these systems and their maintenance helps us choose the right disinfection method for safe, reliable water treatment. Let's now talk about UV disinfection systems and how they work. Ultraviolet radiation damages the genetic material of microorganisms, which effectively prevents them from growing and reproducing. This makes UV systems a powerful tool for water disinfection. Typically, these systems use low-pressure mercury vapor lamps arranged in multi-lamp assemblies, often with quartz sleeves to protect the lamps and watertight electrical connections to ensure safety and durability. The lamps are mounted in racks that are immersed in flowing water, either inside enclosed vessels or in open channels. This setup allows the UV light to directly contact the microorganisms in the water, neutralizing them efficiently. One of the biggest advantages of UV disinfection is that it doesn't require handling chemicals, so there's no risk of chemical safety concerns or creating chlorination byproducts, which can be problematic. Plus, recent technological advances have made these systems more practical and cost-effective, making them a viable option for many water treatment applications. Now, let's look at the operational requirements. To keep the system running effectively, it's important to maintain the proper water level over the lamps, ensuring they are fully immersed. Regularly monitoring the lamp output intensity is also crucial because lamps can decline in performance over time, and they need to be replaced when their effectiveness drops. Managing turbidity levels and flow velocities helps ensure the UV light penetrates the water properly, and frequent bacteriological testing confirms the system's ongoing disinfection performance. Safety is paramount when working with UV systems. UV light can cause serious burns to the eyes and skin, so never look directly into an uncovered UV chamber without protective glasses. Never operate the unit unless the lamps are properly secured, and always handle mercury vapor lamps with care to avoid exposure. It's also important to recognize the limitations of UV disinfection. Since it doesn't leave any chemical residuals, there's no ongoing protection against recontamination once the water leaves the system. Microorganisms can sometimes be reactivated by visible light, and suspended particles can shield organisms from UV exposure. To address these issues, designing high-efficiency systems that maximize the kill rate is essential, especially in water with higher turbidity or contamination levels. By understanding these key points, we can see how UV disinfection fits into a comprehensive water treatment strategy. Powerful, safe, but requiring proper operation and maintenance to be truly effective.